Can you hear me? Yeah? Okay, so thank you very much for the kind invitation to tell you a little bit about what we can do with simulation of many-body localizable, because we don't know yet if they're going to be many-body localized models. So as Bart told you, so how does it work? Yes. I don't have too much time and I have too many slides, but fortunately you can do the work for me because everything is in there. In particular, okay, let me see if I can. Yeah, so complementary to this lecture, this lecture note, the tutorial where you can actually check all the methods, well not all, but some of the methods I will be discussing about. You will be able to discuss, find what are scars and so on by just playing with simple lattice models. And for slightly more complicated codes, which are close to state of the art, there's a GitHub repo, so you can ask me to join it. All right. So as you have seen, to understand many-body localization, it's a technically, analytically, a very complex problem. There's no full analytical treatment of or exact solution, let's say, at finite energy density when you have interaction, strong interaction in disorder, even in 1D. In experiments, you do a beautiful thing, but at some point you are limited because of interactions with the environment. And I'd like to, as an introduction about numerics, of course, I should cite again, like Svetlana has done, this Nobel lecture by Anderson. So she focused on the mathematical aspect. I would like to focus on this indignity of numerical simulation to understand physics. Yes, that's true. It's indignity, but it does not mean that it's simple. So you can be wrong and dirty at the same time. That's possible. So let's try not to do that. So why is it a difficult problem also for numerical simulation, this many-body localization problem? First of all, let me give a few specs of what we would like as outcomes to understand physics of MBL. We would like eigenstates. More precisely, we would like eigenstate in the middle of the spectrum. Ideally, we would like to have method which works in all regimes, in the MBL, in some more thermal regime in the middle. Also, we would like to have something which tells about dynamics, especially after a quench, because this is exactly what happened in the experiment, like in this experimental plot that you have seen. And also, ideally, if we would like to model very much in more detail what happens in experiments, we would like to be able to treat open systems. Of course, that's too much for a single method. And also because it's very difficult. Well, we have to deal with an exponential size of Hilbert space. Well, okay, that's it. Disorder implies that we need to do a lot of disorder averaging in general. So we need cheap methods in some sense, because we have to repeat them 1,000, 10,000 times. Potentially, there's no thermalization. So we can't use thermal method. I will be more precise. And also because we want to work, let's say, at quote, infinite temperature, that means to say in the middle of the spectrum. Unfortunately, I'm coming from condensed matter, let's say. We have developed some nice numerical methods there for many-body physics. They mostly all fail. Why they all fail? Okay, full hexagonalization is because we have, okay, we can diagonalize our matrix. That's fine, but it's limited to small systems. And the MBL problem is full of large finite size effects. Something which I like very much is Monte Carlo or quantum Monte Carlo. Maybe you use that in some problems. You can just forget about that, because when you do in Monte Carlo, you couple to a thermal bath and you just kill immediately MBL. First point. And also, that's more technical, and I will come actually to this technicality a bit later. Methods that we like in condensed matter, they usually go to the low energy physics, like the ground state, what is the first excitation, is it a spin wave, and so on and so forth. And that we can just forget, because that's not the most interesting part. Okay. Yeah?
I understand that the standard Monte Carlo, the HY, something Monte Carlo, but the same thing with Green's function Monte Carlo, or
Yeah, but that's ground state. That's ground state. Nevertheless, the MBL problem made us think, let's say computational physicists, about new methods and new ideas on or to torture our favorite method to make it work for the MBL problem. And that actually created a lot of new methods. I will not cover all of them, but they are listed here. But there are new ideas that really are specialized for the MBL problem, and I will tell you a bit about that. So the goal of this lecture is essentially to provide the bird's eye view. As I said, you will be doing the work because there are some lecture notes to read, some GitHub repo, and very useful. I think you can start playing one by one with this tutorial. It's Python. You could just need to press a button, and you can understand what happens in this localized spin chain in terms of statics, in dynamics. You heard about the PXP model, these cars. You can see them here. And also, if you want to learn about time crystal and quantum circuits, you can really see what's happening on simple model. All right. OK, so if I have to make a rough landscape, so pun intended, on the numerical method of interest for MBL, I would say that there are, let's say, 3 classes of methods. Some, and they don't look at the same thing. So there are some methods which mostly in the thermal phase. That's what we call typicality method, especially for dynamics. For eigenstate, as I said, Monte Carlo or typical method, they just assume thermalization. So they work, but you cannot probe that. There are methods which work only, or mostly only in the localized phase. Some of them are based on this matrix product state representation, and they are based on very deep fundamental properties of MBL eigenstate, which I will be slightly mentioning. There's another class of method which is only work in the MBL phase, which is this unitary flow. I hope I'll be able to cover that, but if not, it's fine. And there are methods which work everywhere, almost everywhere, but unfortunately, they are very expensive. So I've been working a lot on that because you can address all regimes, you can address transition if there is a transition or something like that, but I will try to cover the rest as well. Also, I don't want to cover, okay. Ideally, we would like to methods that are not designed for the thermal phase, not designed for the MBL, but which are designed for a phase transition. So maybe there's a new thing to invent here. It's not there yet. Also, of course, as you know, there's no golden method, otherwise I wouldn't be here. All methods have their own limitation, and I don't want to talk about full diagonalization because this is just so standard. Yeah, yeah. Well, probably its own limitation as well. Mid-spectrum eigenstate. Let's start with that. I want to have a spectrum state in the middle. As I said, in condensed matter, usually we target those low energy states. We have so many methods to talk about that, especially iterative linear algebra, like Langsos algorithm is very standard. There's a tutorial on that. It's very good to know how it works. Just want to see that. DMG, all type of, as Thierry was mentioning, projection, quantum Monte Carlo, blah, blah, blah. Unfortunately, it doesn't work for excited states, or not simply, but we can just try to trigger them a little bit. And the idea is very simple. We will just won't change the eigenstate. We will just change the problem, right? That's very simple to see. I want this eigenstate in my Hamiltonian, those which are like in the middle of the spectrum close to some target. I just need to change the problem. I just need to take another operator which has the same eigenstate, but they are now at the bottom of the spectrum. Very simple. Spectrum folding, you do that, it works. It seems to work. In fact, it doesn't work because, you know, the lever separation here is exponential because that's a many-body system. You have 2 to the L eigenstate that you have to fit in a spectrum which goes like L. So definitely those are exponentially separated, and if you just square that, it's even worse. So any iterative method will fail at some point. It can kind of work on intermediate system size. Something which is much better, and that, of course, connects to the resolvent, the green function, that just takes the invert. Because if this, let's say, orange eigenstate was close to the target, it will be pushed very far in the spectrum of G here. The green one will come here, etc. And the separation will be very large. It will be inversely exponential. Sounds good. There's also another type of thing, which instead of focusing on some specific ordering here, they just target some spectral transform. This is so some special interval here. This is called polynomial filtering. That's Chebyshev type of passband filters. It works well as well. Yeah. Yeah.
How does it scale?
Yeah.
The complexity of this operation and the complexity of finding all.
Yes, yes, you guessed my next slide. Of course, I'm cheating here. The point is we don't compute G. We will never compute G. It's too expensive. Inverting a matrix is actually same scaling as diagonalization. It's even worse actually for some free factors. We don't compute G. Why is that? And well, maybe that's actually that. Let me finish on that. Just for you guys who are interested in Floquet type of system, there is also so Floquet unitary operators. If you have a periodic drive, you have a eigenstates that's well defined. They live on the circle. This is a unitary matrix, and sometimes you're interested in this eigenstate. There's no notion of top or bottom of the spectrum. They are all on the same modulus. There's a nice trick where you just do some this algebraic series, such that these states which were here, like the one you want, you can push them away as far as you want, and then you can use iterative to go to the largest amplitude or method. So let's go in detail, exactly because for the question you asked, Dennis, about the resolvent. Of course, I'm cheating, because if I want to now apply some iterative method, like the Lang's algorithm, power method, where you apply G several times to converge to the ground state of G, well, of course, you don't know G. Otherwise, you wouldn't do that. But iterative method, very important, they only need to be applied, that you know how to apply G. You need to compute the matrix element of G, right? We need to apply G to a vector. Apply G means actually solving this linear system, right? We know Y, and we would like to know what is X. And somehow, this is slightly cheaper than full diagonalization, because we will only need a few of them. We won't need the full thing. So, and there are several. This is a linear system. This is well defined. Matrix H is sparse. It's very important also to mention that. So, out of we deal with matrices which are 1 million by 1 million, but in fact they only have, I don't know, 10 million non-zero matrix elements, something like that. This is very, very sparse, mostly zeros. And then solving linear system with mostly zeros, well, we know how to do that. We can use iterative solver. So at every time you want to apply G, you solve iteratively a linear problem, and then you solve another one at the next iteration, etc. But something which works well is very brute force stupid method. Actually, if you talk to the guy who are doing that, they are really not stupid, but this sparse direct solver. So the idea is very simple. You use a LU decomposition of your matrix H minus sigma. That means you just it's just like a triangular lower. U is the upper triangular. And solving, once you have this decomposition, then you can easily solve by these chains with the upper and lower descent, this type of problem. It requires a lot of memory, because the matrix, the LU, that's called the factors, they are sparse, but much less sparser than H. Still, it works fine. So there's a code in the repo, and also in this work that we have done, where this method is explained in very large detail. Okay, let's assume that we can solve that. What do we get? So let's give you some typical numbers so that you have things in mind. So you have this spin chain, which is like the prototypical model of MBL that you have been talking about. You have heard about it in fermionic language, but it's the same. It's just really the same. So this is the chain size we can do right now with this LU method. So this is the size of matrix we are dealing with. And this is the number of non-zero. So you see that's not a big deal, but in the end it starts to be a bit, you have to live with that. And this is the kind of results that you obtain. You do the subset diagonalization, you have the eigenstate, you have the spectrostatic, and so on. You work them out. Actually, you will do that in this small tutorial. And we kind of obtain this phase diagram, where this is the energy density. So ground state is not here. It would be here in this thing. And this is the disorder. And at strong disorder, we see some property of localization. And at low disorder, we see that. And that's possibly from what we see in the numerics, an edge. So we did that 8 years ago. It took us 200 years to do that on the CPU, of course. No, it's much more less, and because there have been some improvement in the solver, which we like very much. And now you can almost do that. Yeah, this one in a few days of calculation, actually. Let's say a few weeks. Not on so large supercomputers. Okay. If you don't want to do that, and the code, there's almost a production code here in the repo. If you don't want to do that yourself, there are some wrappers around that type of code, which exist here. Okay, so you can really do that. It's not too difficult.
Can I ask a question? A very stupid one. How do you decide numerically in a finite size system whether you have a according state or
okay, yeah. We look at spectral statistics. We look at entanglement properties. At IPRs, and we try to.
Localization stuff.
Well, yeah, that's what we're asking. Yeah. Well, entanglement is not standard localization stuff. So we check for area law. This is actually these symbols are different markers.
So you mean scaling of entropy with size?
Exactly. Exactly. Fine size scaling. Yes. Of course. We have to deal with very small system. Oh, I see you laughing, but this is much better than the best Anderson localization problem ever. So, all right.
With Schreiber, it was 100 in the beginning.
Sorry?
With Michael Schreiber in the beginning of Anderson and even directions, it's 100.
No. Well, you have to be careful. You mean matrix size? You know, if you go in 3D, that's L cube. So that's like a 256 to the cube, which is roughly the record, I think, in Anderson localization. On top of which, we have much more zeros. The graph is much more complicated than just a 3D graph, which is actually a killer for this type of method. Okay, so we have a big supercomputer. Actually, I'm arguing that you can almost do L equal 20. You can do that on your laptop, actually, with this code, which is kind of reasonable. This, for up to 24, you need a supercomputer, but you can do it. This is like brute force. We can do the full phase diagram. We are not limited to ergodic or MBL. There are another family of methods. I forgot to press on the button. How am I doing with time?
Oh, yes, fine. You have 20 more minutes.
Okay. So there's another family of methods, which is called matrix product state and matrix product operator. Some of you guys are familiar with that. I will not do the full formalism. I will just give you one picture to have an idea, and then I will tell you how we can design MPS method for the MBL problem. So matrix product state is an ansatz in some sense for a wave function. So we have a many-body wave function like a spin chain. So let's say we have n spins, and you can form a basis of up and down that are 2 to the n state. And the matrix product state is an ansatz for the coefficient of the 2 to the n state. And you assume that the coefficient, so that's a graphical representation of this wave function. At each leg you have it can be up or down. It assumes it takes the coefficient takes a form of a matrix product. At each side I will put 2 matrices, one for up and one for down. And I assume that these matrices, they are small. They are chi by chi, where chi is some number. You can play with that. And I do this product graphically. It's a contraction. Like you put a line for the contraction. That's a way to represent matrix product. So that's an ansatz. It's very good for 1D ground states in many-body physics. But it has, of course, it has much less coefficient than the 2 to the n coefficient, because you only need to know the matrix. If the system is translation invariant, actually, you can assume that the same matrix, or the same set of 2 matrices at each side. For MBL, of course, there's disorder, so you cannot do that. But there are very small numbers, polynomially small numbers, right? Instead of exponentially small number. Of course, you have to pay something, and the thing you have to pay in this ansatz is that actually you can see that if you just cut a link here, the maximum entanglement between the left and the right is related to this chi number. It's a log of chi max. So assume chi is typical numbers, I don't know, 64, 100, 1,000, maybe a couple of thousand. Essentially, it implies that you can only describe area law state. You cannot have a volume entanglement. So, yeah, there was a question? No? Okay, so this is some form of Maliev state, and we will use them, and that's very important because in the MBL phase, I told you, so it works very well for 1D spin chain, ground state, and so on, like we do in condensed matter. But we know it will fail for excited states if they have a volume low entanglement. If they have a large amount of entanglement, forget it. But we are saved by physics, because in the MBL phase, as Valentina has mentioned, all eigenstates, all of them, in the middle of the spectrum, they all have area law. Lowly entangled state. And that's a nice argument here, which I would like to copy from this paper. So how can we see that? Why this form could be useful? So let's imagine I have a single partition Anderson localized state, just to, for the sake of the argument, with some localized orbitals. They are occupied or not. So they are either in the ground state or excited state at each orbital. So let me construct, like a Slater determinant, if you want, a product state, many-body wave function with n of such orbitals. Well, you can say at each site, I can make a product wave function where it's either the ground state which is occupied or the excited state of the orbital. Okay. So the MPS on that, it's a many-body version of this on that, where you replace this thing by just matrices, small dimension matrices. That's a way to see that. And exactly, you can use this formalism. And the idea, the ground state, is that it's the product of G matrices, and state in the middle of the spectrum would be sometimes E, sometimes G, and so on. That's a way to have a picture for why this type of MPS is valid for MBL. Okay? No, that's good. We kind of know that we have the good family of states to describe perhaps this MBL eigenstate deep in the middle of the spectrum, but how do we get them? How do we get the exact coefficient of this MPS? Well, the idea is that we can torture some well-known method for the ground state, and we can torture it to spit out excited many matrix product state. So, first idea is very simple. We just, again, change the Hamiltonian. We change the problem. Instead of working with H, we work with the ground state of H minus sigma square. That's done here. Or you can also work with the ground state of H minus sigma minus 1, exactly like we did in exactization. Okay, it works. There's a further idea, which was developed in this work. Okay, so this is some strange-looking picture. If you haven't seen them, you can say that. That's a way to actually optimize locally your small matrices, so that it spits out the correct, and you sweep, and that's the constant algorithm. Let me, don't give details, but at some point you have to minimize an effective Hamiltonian, a local, you have to optimize an tensor so that it is the ground state of a small Hamiltonian. So the big idea in this work is that instead of doing that, instead of trying to minimize the energy at every local matrix, we will not do that. We will actually follow, we will take the eigenstate of that small matrix, which has the largest overlap with a single product state. So what does it mean? It means that we follow the large disorder, let's say we follow the Lyum, the local integral of motion. And that's a really clever idea. And then we can obtain very efficiently, we don't get the full spectrum, all eigenstates one by one in the middle of the spectrum, we get some of them. The one which have the largest overlap, because it's almost a one-to-one connection between a simple product state and this matrix product state. And that's a very nice idea. We can do more. So I tell you that every eigenstate is a MPS, a matrix product state. But there's more. We can ask for the full unitary diagonalization to have also a matrix product form. And this is no longer called a matrix product state because this is a matrix. It's a matrix product operator. I'll spare the details, but the idea is that we can find a single set of tensor which represents the full diagonalization operation. And that's just wonderful. If you think about it, never in quantum many-body physics you can do some local thing and you completely diagonalize the Hamiltonian in one shot. That's just a very specific property of the MBL phase. Now, of course, this can be proved at some level of rigor. Not perfect, but it's very clear that in the Lyon picture, this is the correct thing. And this is stronger than to say that every eigenstate is an MPS. It means that all these MPS can be obtained from a single tensor. It's slightly, it's better. Then there comes the question of, well, how do you find it in practice on a lattice model? It's slightly more complicated, but there are some ideas on how to do that, and they are very competitive. If you are in the MBL phase, they completely fail if you are in thermal phase, and that's very well understood because then you have volume law entanglement. Okay. So there was ED, shift invert ED, which is valid in the full phase diagram. There's this matrix product method, which are valid in the MBL phase. Let's see another family of methods which allows to get eigenstate in the MBL phase. I will go quickly through that. I will just give you the idea. Is in some sense we try to do numerically what Imbri has done analytically. We try to connect, or let's say spin chain Hamiltonian, to some L-bit Hamiltonian. We try to construct this unitary transform to get to this target Lyons Hamiltonian, where it's diagonal. Here it's not diagonal, it's sparse. And here, and let's imagine we can imagine there's a continuous parameter L, which I will be discussing about. This is a flow parameter, and at L equals 0, we are in our favorite lattice Hamiltonian. L equals infinity, we have done the job of Imbri. It's not the same expansion because there are many ways to do this parameterization of the flow. So the idea is that we want to kill all of diagonal elements, and it's a well-known method. Wegener invented it a long time ago. It has been applied to many-body physics. We can parameterize this flow by some generator, eta, in such a way. And you have some simple rules for the observable angular flow. And we have the liberty of choosing eta in some sense, and we try to see what it gives. One simple choice, perhaps not the most optimal, is that you choose eta, which just wants to kill, all of the diagonal element in the process. There's an you try to do that, yes, that's what you want to do. You don't, well, let me give us, so all you do that, you have some target Hamiltonian, you parameterize the running Hamiltonian, the one which you get in the middle, in terms of the lerms, and you have some parameter, and you try to solve some nonlinear differential equations which are coupled, and you can do that. You do an approximation because you cut the rest here, but if you do that, you can have some kind of self-consistent way of trying to do that. And sometimes it will fail. You don't always see it, but I think it's a very nice idea, and there's a nice review about that. So let me just give you some results about that. So basically, in doing so, you can do that for the Hamiltonian, but you can do that for any observable. So you can indeed start from your spin and see how it became a Lyon. For instance, you can look at what is the spread of the final tau IZ that Valentina was discussing about in terms of the original spins, and you see that it has spread a little bit around 5 sites. That's a way to construct them. Of course, that's for large disorder. The method will always do some diagonalization in the end, but what you see is that if you do that at very small disorder, the spread of the is just, so it doesn't mean anything. It's no longer local. That's a way, one way, as Valentina mentioned. There are several ways of obtaining these lyomes, so this is one way of doing that. And you can try to do some nice physics and so on. So one point, once again, it's well controlled only in the MBL phase. And if you look at the spectral statistics that you obtain in the end, it's always MBL. So you don't really know. It will not work in the thermal phase, but you don't always see why. All right. Any question? So far I've worked on, let's try to get this eigenstate. But in the experiment, we don't do that. We do dynamics. So now the last part of my talk will be about dynamics. Any question on eigenstates in numerics?
This matrix product thing.
Yeah.
You have transitions within the MBL phase where you change bases on which you
Yeah. Well, there's no longer any example of that. There's always there's a metallic phase. So I guess, well, yeah. The problem is that you see that things go out of control, the bond dimension explodes and so on. I guess that's what will happen. In the remaining 15 minutes, is that less than that?
Yes, less than that.
Okay, let me say a few words about this thing. So, this is a question we want to solve if you want to do a dynamics of an isolated system with some Hamiltonian H. So if I ask you the question, how do you do that? If I give you H, how do you do that? If you think, you don't have to reply, but if you think that, well, I just diagonalize H and then I do the exponential and just, okay. Don't do that. You don't want to diagonalize H. You just want to apply the exponential of the matrix to a vector. This is much cheaper. You don't want to form this exponential. You just want to apply it. That's the key. Okay, if you do that naively, you can do the expansion, assume t is small and blah blah, and it should work. It's an exponential. It has a finite radius. Radius of convergence is infinite. But it's very unstable. There are some funny examples of 2x2 matrices where you take the exponential, and if you take k to be 60, it just fails miserably. Of course, these matrices, there's a funny paper which is called 19 dubious way of computing the exponential of an operator in finite precision arithmetic. This is very funny. But there's a nice idea which we come from our background on the long source algorithm, iterative and so on. This is called the Krylov space. The Krylov space is very simple. You just take your initial state, you apply the Hamiltonian, you get another state, you apply the Hamiltonian, you get another state, and so on. And you do, how do you call that, the span of that. You don't take this state, you just take the space generated by this thing. The orthogonal space generated by this. This is called the Krylov space. This is standard in numerical linear algebra. And if you do this expansion, in this space, it's much better. It's sort of exactly what the long source algorithm does. It constructs this space for you. It makes an orthogonal basis for this space. That are the long source vectors, in such a way that your Hamiltonian is, what do you call that? Similar orthogonal similarity transform to a simple matrix which is tridiagonal. And if you use that, this is exactly what the long source algorithm does. You can then just apply this, and you obtain a very simple formula. You have the V, which is a column which are these vectors here, which you generate by doing this algorithm. This is a T matrix. This time you can diagonalize it because it's very small. It's like so pictures like capital N is like 1 million or 1 billion. We can do that, and N is 200. Small n is 200. So that's easy to diagonalize, but you cannot diagonalize a 1 billion by 1 billion matrix. If you do that, that's very simple. You can just follow. And of course, the number n depends on how far you want to go in time, because there's some error that you make here. But the idea is very simple. You just repeat it. You do this thing, right? Every tau equal 1, let's say, you just do this transform. And for this, you only need to know how to apply h. Okay, so that's it. To apply the exponential, I need to know only to apply h. It works well. There's a code about that. This is the same idea, essentially, as the Langsos algorithm. What do you obtain? Well, we did that for chains of course, and then I should have said, if you have this wave function, you can compute any observable in that. You can compute the imbalance, which is measured in the experiment. That's a nice way to connect, without having the eigenstate, to connect the experiment to the experiment. So you can compute the imbalance as a function of time. Of course, at some point, you stop doing that because it converges, or you know what you're going to get. And you can do that on chains which are of size 28, 30, something like that. So matrices which are 1 billion by 1 billion, essentially. It works well. It allows you to clearly distinguish some initial signal which just saturates at long time from something which will eventually go to 0, not the log scale here. What is nice, as you can see, it works in all phases. Ergodic and MBL, I can do this thing. So it's an exercise for you if you want to complete something more complicated than the imbalance. There's something which is called the octobre. Let me skip that. And let me just say that you can do the same time evolution within the matrix product state formalism. You apply some trotter thing, and this MPS thing is just very nice to apply gate exactly like you need to do. There's also a code based on that. Nevertheless, something very important, once again, this will work only if the entanglement of the final state at time t is small. Otherwise, it will fail. It only works in the MBL phase. And you get something like the log. And that's good, because we know that in the MBL phase, the entanglement growth is slow. It's a logarithm. So you see after time 1000, the entanglement is just 0.35, which is like you need the matrix product state of size. The matrices are 2 by 2, essentially, roughly speaking. I'm exaggerating, but there's very small matrices in this matrix product concept. And if you crank up the numerics, you augment the size of the matrices, you can almost go to the ETH phase on finite size. Actually, that's some debate about this thing, but you can crank up the thing a little bit. You can do that also. All this unitary flow thing, you can also do that for dynamics. You just need to follow. It's very nice. Let me just finish on that. You do this unitary transformation. That's here. You flow back. You follow the eigenstate, the observable you want, also along the flow of the Hamiltonian. You evolve it in the diagonal basis. That's very easy, because evolving in the diagonal, just taking the exponential of a diagonal. And then you flow it back to the original time, to the original basis to do a measurement. That's a very nice idea. And again, you can do numerics in the MBL phase thanks to this unitary flow. I think...
This is more or less the Heisenberg picture, right?
Yeah.
Pre-evolution, you know, and...
Yes, that's a way to formulate it, but the fact, well, this unitary transform is this is the Heisenberg picture here, but you first have to go to the diagonal basis in some sense. Well, yeah, if you want. But going to the diagonal basis is, of course, the most expensive thing here. Let me skip open system. If you're interested, we can do something about coupling the system to an environment, and we will use matrix product operator. So we want to solve essentially what Dennis has mentioned, the Lindbergh equation. Those are matrices, so we need a matrix product on that, matrix product operator on that. And we can do that as well with this type of... it helps you find some transport properties. And very funnily, it works at the same time. Some formulation work close to equilibrium in the ergodic phase, and some of them allows you to, for instance, to compute loss or dephasing only within the MBL phase. So it's funny, this state of difference. Okay, so I won't be talking about, you can think about other methods. I will be delighted to talk to you about why quantum Monte Carlo fails, no matter what you do. In this thing, you have other methods, some of them which I don't understand very well, but they also use the matrix product parameter. And I will just finish on time. Is that almost okay? On the indices scale, actually, there's a lot of room for you to do some nice numerics. You can be very strict, or you can just want to calculate things. Many things to be done yet in numerics. Thank you very much.